Yesterday in class we started some basic definitions, definition of a midpoint, of segment bisector, angle bisector, and now I'm going to show you how to apply these things in a little baby proof, because that's what we're going to need them for. So in each of the following, you're given information, and you have to interpret what the information means by first marking the diagram and then writing it in proof form. So here's the first one. I'm given that D is the midpoint of AC. So if I look at this, D is the midpoint of AC. Therefore, I'm going to mark off my two congruent segments, and I'm going to write a congruent statement from that. Because those two are equal in measure, I can write AD, and I'm going to write a little bit bigger than what I have here. It's congruent, because I can't write in this tiny spot, to CD. AD is congruent to CD, and my reason is a midpoint divides a segment in half. A midpoint divides a segment in half. That's my definition of midpoint. So let's look at the second one. This time I'm given that BD bisects segment AC. So we have to be careful. I know a lot of times we think of bisect and we think of the angle, but look at what I'm bisecting. It is a segment right here. Okay? So again, I'm going to mark it the same way. I'm going to have my two marks that signify congruence, and I can again say that AD is congruent to CD. This time a segment bisector. A bisector divides a segment in half. So we have two different things that can cut things in half. And my writing is not very good here, bear with me. A bisector divides a segment in half. In half. Okay? In the next example, I'm given that BD bisects angle ABC, so that's different. Now we have an angle bisector, so here's ABC, and BD is bisecting it. So these two angles are going to be congruent. Therefore, I'm going to mark them like that. Let's see how well I can do this on my thing. So those curves in there denote the fact that those two angles are going to be congruent. Because of that, I can say that angle ABD is going to be congruent to angle CBD. B is the vertex for the congruent angles. So angle ABD is congruent to angle CBD. And this is an angle bisector. An angle bisector divides an angle in half. Divides an angle in half. And then finally we have BD is perpendicular to AC. BD is perpendicular to AC. That's going to give me two statements that I can use. First of all, I can say that these angles are right angles. So I'm going to mark it that way. And then I can also say that they are congruent, the two angles. So I have to put that in there. So once I'm given that BD is perpendicular to AC, we know that perpendicular lines form right angles. So I can say that angle BDA and angle BDC are right angles. I'm going to have to write over the number 3 here. Okay, perpendicular lines form right angles. That's my reason. Once you say that, you can add one more statement, and you can say that angle BDA is congruent to angle BDC. That's because, for number 3 here, right angles are congruent. So those are some reasons we're going to use, statements and reasons, when we start building our proofs coming up in the next couple of lessons. Now we also have some other useful properties that we've talked about and we're going to be using in proofs. So the first one is the addition postulate. Equals added to equals are equal. So, and the same thing goes with congruence. So if I have if AB is equal to CD, and then AB plus EF is going to be equal to CD plus EF. So if you have congruent things and you add them together, you still have a congruent thing. Same with the subtraction postulate. Again, if I start with AB is equal to CD, then I can say that AB minus EF is equal to CD minus EF, and that will also lead to another congruence. So we're going to use that when we have to break apart angles and segments and put them back together again. All right, the multiplication postulate and the division postulates are handy when we have doubles or halves of things. So the multiplication postulate says equals multiplied by equals are equal. So again, if I have AB is equal to CD, then I can say, well, if you double it, that's going to be equal to 2 times CD. So equals multiplied by equals are equal. Same with halves. Or divided by things. If AB is equal to CD, then half of AB is equal to half of CD, for example. Just for an example, it works for multiplication or division. And we've used the substitution property before. A quantity may be substituted for an equal quantity. So that's going to be, if two things are equal to the same thing, they're equal to each other. If A is equal to B, and B is equal to C, by substitution, you can say A is equal to C. Okay? And then anything is equal to itself. You can say AB is equal to AB, or segment AB is congruent to segment AB. We actually use the reflexive property quite a bit. Now finally, there's parallel lines I want to remind you of. Usually we'll use alternate interior angles or corresponding angles. So we can say with parallel lines, or if two lines are parallel, we know that corresponding angles, we're going to say congruent this time because that's what we're going to start using. Corresponding angles are congruent. And then finally, again, with parallel lines, alternate interior angles are congruent. So all of this is kind of pre-work to build a foundation, to put them all together and write some proofs. So we'll be starting with some basic proofs in class and building from there. So this is a great reference sheet for you to use while you work on problems independently.